All right, welcome back to Graph Theory. This video, we're going to be talking about some ideas in section 4.2 on connectedness. You're looking at the goals of the lecture there. My main goal is to introduce some notions for you to think about in terms of this business. So I'm going to introduce what is called a cut vertex in a graph, a bridge, also the vertex and edge connectivity of the graph. I want to discuss and prove some elementary properties of connectivity, explore them in some examples as we go. And then not prove in this video, but discuss the statement of Theorem 4.5. I think including the proof here is going to make this video a little bit too long, but maybe we can prove it while we're in our virtual class. Couple disclaimers before we get started here. The first one, there's a lot of material in section 4.2 that I won't be explicitly discussing here. I'm kind of choosing to move on and show you kind of a more broad range of topics in graph theory rather than going too deep in any one of them. So we won't spend more than just this one video lecture in 4.2. But if any of this business is interesting, you can certainly feel free to ask me about it. We could have a conversation outside of class where I can point you to some references or just talk to you about any of these ideas. Just to kind of motivate it, why we're talking about connectedness. One of my favorite graph theory authors is a guy named Doug West. He's at Urbana-Champaign. And he starts his section in his textbook on connectivity by kind of talking about networks, communication networks. And that's a very broad idea. Maybe it's a computer network. Maybe it's a network of people hooked up by some kind of communication device. Maybe it's a distribution network, little physical supply lines. So by communication network, I mean something very broad. But the nodes in the network represent the entities that want to communicate with each other, and edges would represent whether they can communicate. And Doug West, and I believe this, says that a good communication network should be hard to disrupt. What does that mean? If you're thinking about this communication network as a graph, if we lost vertices or edges in the graph, we still want the information to flow around. Typically, edges would correspond to costs, building pipelines or running wires or cables or something like that. So we'd like to have as few edges as possible. So in other words, in many interesting contexts where you're building these networks, communication networks, you're generically interested in this question: how far away is your graph being from disconnected? How many vertices and edges could go down before we wouldn't be able to communicate with each other anymore? All right, so that's just kind of a real quick motivation for why people would start thinking about such notions. All right, let's get into some mathematics. First notion I want to tell you about is something called a cut vertex in a graph. Okay, so what is a cut vertex? It's a vertex in a graph that when you remove it, you have increased the number of connected components in the graph. All right, so pulling out this vertex makes the graph have more connected components. I'll recall to you that when we remove a vertex from a graph, we also remove all the edges incident with it. You can't have an edge that doesn't have two vertices. Let's look at this example. I've got a nice little graph drawn here. You can already start thinking about some of its cut vertices. I just want to replicate it a couple of times so we can play around with it. So I'll give myself 3 copies of this graph. And then, well, it's written there that V is a cut vertex. Yeah. So maybe you've already convinced yourself of that, but let me just sort of do it in a little animation. The recipe is, okay, remove V. There goes its label. And when you remove V, you can't leave those 4 edges there without a vertex on that end, so they have to go. And sure enough, you can see that the graph G minus V, its number of connected components went up. It now has 2. There's 2 connected components, so V is a cut vertex. So is X. Yeah, you pull the vertex X out of the graph. Oops. Pull the vertex X out of the graph. You have to take away the edges that were incident with it. It's got 2 connected components. This isolated Z over here is one of the components. It has no edges. That's okay. The other component is this 3 cycle with an edge stuck on it. Yeah. So sorry, that's G minus X. G minus X is the graph I've drawn there. This third picture is just to try to convince you of this last statement, that the other vertices aren't cut vertices. You can choose any one you like. If you were here, I'd let you choose it, but I'm just going to choose for you because you're not here. I'll pick W. So pull out W, take the edges that were incident with it. I have not increased the number of components in that graph. The graph G minus W is still connected. So W is not a cut vertex. Neither is Y, neither is U, and neither is Z. You can check that out. Okay, so cut vertex. In a big graph, it's certainly not going to be easy to just glance at it and see what's a cut vertex, but the notion is not that hard to understand. Here's some kind of related notions to this. We won't get too deep into these things, but I want to use them a little bit. So the first one is the so-called vertex connectivity of a graph. It's denoted by this kappa of G. In my handwriting, that kappa looks like a K, but if you look closely in your book, it's not a K, it's the lowercase Greek letter kappa. Kappa of G is the vertex connectivity. And what is it? It's the minimal number of vertices that you need to remove to disconnect your graph. Or there's one graph for which that's not ever possible. There's one graph that you cannot remove a sufficient number of vertices to disconnect it. So to include that one, I'm going to throw in this or. So it's minimum number of vertices that you need to remove to disconnect it, or to just leave you with a trivial graph with just one vertex. Okay, that's called the vertex connectivity. If G, what do I mean by G being K connected? K is some natural number. It's K connected if its vertex connectivity is at least K. Okay, so you're 2 connected if it takes at least 2 vertices to get removed to disconnect you. So it's sort of a measure of how connected you are. If you're K connected for big K, it means you have to destroy a lot of vertices before you would disconnect that graph. So in terms of your communication network, you'd like to design one that was K connected for a pretty big K if you were ever worried about losing vertices. These will just be some exercises. Maybe they'll show up as formal exercises in the next homework set. Maybe I'll just leave them as informal exercises, but just to get used to the terminology. The only way that the connectivity of a graph could be 0 is if it was disconnected to begin with. Yeah, you don't have to remove any vertices to disconnect a disconnected graph. Likewise, I could define this notion of cut vertex. A graph has a cut vertex if and only if its connectivity is 1. Because if you disconnect the graph by removing one vertex, then you can certainly do it by removing more. So the connectivity would be equal to 1. This is kind of an interesting example, and it's the reason why we have to have this annoying or it leaves just one vertex. If you take a complete graph, you won't disconnect it ever, actually, by removing vertices, but you will reduce it to a single vertex after you remove all n-1 others. Yeah, so I've drawn a little picture here at K4, and we can again kind of watch. Let me pick any one of the vertices. They're all kind of symmetric. I'll pick this one in K4 and remove it, and then I have to remove all the edges incident with it. And you're probably not surprised when you remove a vertex from a complete graph Kn. Well, you're left with the complete graph Kn-1. So we have a K3 here, and then I remove a vertex. Take the edges with it. I get a K2, remove a vertex and the edge, and I get a K1, just one vertex. So that ended up taking 3 vertices to get removed. So the connectivity of K4 was 3. All right. If your graph isn't complete, its connectivity is never more than 2 less than the vertex set. You never have to remove more than all but 2 of the vertices to disconnect a graph, unless it's complete. If the graph is complete, you need to take that one extra step. All right, so you can ask me about those things when we're Zooming on Friday, or you can ask me in an email. You can ask me anytime you want. Okay, so that was a couple of our terms. Cut vertex, vertex connectivity. Let's talk about bridges. What's a bridge? We talked about this when we talked about trees. An edge is called a bridge if when you remove it, you increase the number of components. All right, so it's the exact kind of analog to a cut vertex, but we're taking edges out. All right, in our example graph here, there's just one bridge. When you take an edge, that's it. You just take the edge. You don't take any other vertices. So looking at that example graph, I'll just do it here. But if I remove the edge XZ, I called it E for short, but it's that edge right there, then I've disconnected that graph. So it's a bridge. You can glance at the graph that remains. No other edge will disconnect that thing. Every other edge is on a cycle, so they can't be bridges. Great. Okay, the analog of vertex connectivity is edge connectivity. The edge connectivity is the minimal number of edges necessary to disconnect the graph, right? Or again, a caveat makes it trivial. That's just so that the trivial graph K1 has an edge connectivity because it doesn't have any edges at all. Cool. So lambda of G is how our author denotes this. Most graph theory books actually denote it by kappa prime, but our book denotes it by lambda. That's the Greek letter lambda, and you gotta remember to put your B in lambda. Cool. Again, some just kind of observations. I'm not going to prove them here. You can think about them, but or actually, sorry, it says the first one is something we just proved in the past, that every edge in a tree is a bridge. In fact, a connected graph with that property, I believe we proved, is a tree. So if you have a connected graph where every edge is a bridge, you have to have a tree. So in particular, the edge connectivity of a tree is 1. Yeah, every tree has edge connectivity 1. One edge destroys the network communication. Okay, so let's prove a theorem about cut vertices. You can see the statement of the theorem there. I'm going to take a connected graph, and then the heart of the theorem is that a vertex in that graph is a cut vertex if and only if you can find a pair of vertices such that your cut vertex is on every single path between them. Every single path between them. I think I've got our example down here at the bottom of the proof, but you remember that V was a cut vertex in this graph. And you can kind of see there's lots of pairs of vertices, but for example, if you took, I don't know, the vertex W and the vertex Z, for example, or sorry, let me use the same notation as in the theorem. Let me take U and W. Take the vertices U and W. Every single path between U and W in that graph contains V. Yeah. So the theorem says that such a pair of vertices U and W have to exist if V is a cut vertex. If you switch your notion, look at the cut vertex X. Well, U and V are not the pair anymore because there's a UV path that doesn't go through X. But you could take Z and any other vertex in the graph, and every path from Z to any other vertex has to go through X. So it's sort of a way to look for cut vertices, if you like. If you could kind of easily spot, like, oh, every path between these two places actually has to go through that vertex. That's a cut vertex. Okay, so let's take a look at the proof, just to give you some ideas of tools you could use to prove stuff like this. It's an if and only if proof. So let's start by assuming that I've got a cut vertex, okay? Well, what's that mean? By definition, it means that because G is a connected graph, removing this cut vertex disconnects it. Okay, so if you have a disconnected graph, you can pick a couple of vertices that are in distinct components. That's the whole idea, is pick U and W so that in the graph G minus V, those are in different connected components. Okay, so G is a connected graph. So take any path P that connects this U and W in G. Yeah, I know that there's at least such one path because G is connected. There might be any. Take any one you want. Our cut vertex has to be on that path. It has to be in the edge set of that path, because if it weren't, then that path would be a path that should say G minus V. It would be a path in G minus V. Yeah, if there was a path between U and W that didn't go through V, then that path would be in G minus V by definition, but that would mean that U and W were in the same component, and we picked them in different components. All right, so V has to be on that path. Conversely, if we had a pair of vertices and every single path in G went through some vertex V, right? So I have this vertex V, every path between these other two vertices goes through it, then there couldn't be a path in G minus V, a UW path in G minus V, right? Because we're saying every UW path has V on it. Well, so then you couldn't have a UW path without V on it. That's all I mean by that there's no UW path in G minus V. So if there's no UW path, then G minus V must be a disconnected graph. There's a pair of vertices that doesn't have a path between it. So pulling out V increased the number of components. That means V is a cut vertex. All right, so that's the proof of the theorem. We already looked at this example, but again, you can kind of look at it stop the video if you want to, but every path between U and W goes through V. Every path between Z and any vertex that you like other than X goes through X. So those are both cut vertices. If you want to see a demonstration earlier, we said, right, we said W is not a cut vertex. So you'll have to think about this, but there is not a pair of vertices in that graph for which every path between them goes through W. You can't find such a pair of vertices. You give me a pair of vertices, there must be a path between them that avoids W. And you can kind of see it's obviously true, but cool. Okay. I'm going to leave this one to you. It's kind of the edge disconnecting cousin of the theorem that we just proved. But if you take a connected graph, then an edge E is going to be a bridge if and only if there is a pair of vertices that every UV path between them goes along that edge. So maybe that'll show up in homework 8. I got to get homework 8 ready to post tomorrow. So it's good that I'm throwing all these ideas out there. Okay. One more theorem in this video lecture. Let's see if I can try to just walk you through it real quick to keep the video kind of short, and then you can ask me questions about it. So what's the theorem? The theorem says that if you take a non-trivial graph, it has at least 2 vertices that aren't cut vertices. All right. So every non-trivial graph has to have at least 2 vertices that when you pull them out, you're not going to change the number of connected components. Okay. So let's walk through this proof, and you can ask me about the details when we meet. So first of all, without loss of generality, that's what my WOLOG means. I'm going to assume G is connected. If G is not a connected graph, then I'll just apply this construction that I'm going to do below to a connected component of it. Okay, so I might as well just assume my graph is connected. And it's going to be a proof by contradiction. I'm going to suppose for a contradiction that G has at most 1 vertex that's not a cut vertex. All right, so G has at most 1 vertex that's not a cut vertex. If you look at all the vertices in this graph, they're all cut vertices except for possibly one of them. That's the negation of this statement. Cool. All right, so using some ideas from our work in distance, pick a couple of antipodal vertices, okay? Let's look at this picture while we do this. So picking a pair, I know that there's a pair of antipodal vertices in a graph. The distance between them is the diameter, it's the maximum eccentricity, and I know that there's always a pair of antipodes. We proved it, okay? We're assuming that this graph has at most 1 vertex that isn't a cut vertex. So one of those 2 vertices, U and V, has to be a cut vertex without loss of generality. Let's say it's V. They both can't be non-cut vertices. That's the assumption I'm making. So we might as well assume it's V. Cool. All right, and now, like the picture kind of suggests, pick a vertex W that's in a component. I should be more specific here. A component of G minus V because G is connected, a component of G minus V that's different than U. V is a cut vertex, so pulling it out disconnects the graph. It must be possible to find vertices U and W that are in different components. So my little circles here are just kind of schematic ways of indicating that those things are connected components, and U and V are in different connected components. Okay? Cool. Well, not directly by our previous proof, but from the idea in it. U and W are in different components of G minus V. So every UW path in G, again, let me emphasize that, has to contain the vertex V. Because if there were a UW path in G that avoided V, then U and W would be in the same component in the graph G minus V, and we're saying that they're not. Okay? So what would that mean? Every UW path contains V. Well, that means that the distance from U to W would have to be bigger than the distance from U to V, because no matter what path you take, and in particular a geodesic, as you start marching your way from U to W, you have to go through V. So you're going to move along the distance from U to V and then some, right? So that distance is going to be bigger. But that means that we found some points, vertices, U and W, that are further away from each other than the diameter of the graph, and that's our contradiction. Okay, so that's the proof. I hope you'll ask me about it in class. And then I'm just going to end by not proving, but stating and kind of illustrating with an example. Let me hide the example a little bit from you. Theorem 4.5, it's a theorem by Whitney, an old theorem. It was proved in the 1930s, 1932. It's got a little piece of notation in it that I haven't said anything about. So let me remind you in our book that lowercase delta, I'm getting a little full of Greek letters too, but let's handle one more. Lowercase delta of a graph is just the author's notation for the minimum vertex degree. So you look at all the degrees of the vertices in the graph, and the smallest one, and there may be many of them, is called delta of G, right? Like for example, delta of a tree is 1, delta of a cycle is 2, delta of the complete graph Kn is n minus 1, and so on. So it's the minimal vertex degree. And what theorem 4.5 says is that if you take a connected graph, and I believe this is true for more arbitrary graphs, but let's just state it for connected graphs, that the vertex connectivity, the minimum number of vertices that you need to remove to disconnect the graph, is never more than the edge connectivity, the minimum number of edges that you need to remove. Yeah, so you could always destroy a network with fewer vertices than you can edges. And in particular, that number of edges would never need to exceed the minimum degree of the vertices in the graph. All right, so this gives you some sort of useful bounds in computing these numbers, because computing kappa of G, lambda of G, it can be non-trivial. I don't really know much about the actual computational complexity, computer science aspect of that. Maybe one of you would give a guest lecture in this class and tell us about the ins and outs of algorithmically computing these connectivity numbers. It's out of my realm of expertise. Here, let's end. This video is getting long. I've got a quick example down here just so you can kind of think about what these things mean. It gives you another chance to practice. I'm going to let you do the verification, but I've drawn a nice graph G there. I like it. It looks like a house with a kite on it or something like that turned on its side. And please check, pause the video, take just a few more minutes, that the vertex connectivity of that graph is 1. That graph has a cut vertex. Its edge connectivity is 2. And you can check at a glance that its minimum vertex degree is 3. So I just wanted to point out that these inequalities up there in that theorem can be made strict. Yeah, this is an example where the vertex connectivity is strictly less than the edge connectivity, which is strictly less than the minimum. Okay, so I hope that some of this was useful for you, and I will see you in class. Thanks.